All right, hey everybody. In this video, we are going to continue looking at parametrized equations. Specifically, we are going to look at a great example, the second example that we've seen, but one that is an absolute classic example involving our basic trig functions, sine and cosine. So specifically, I am going to let my parametric equations be as follows. So I've got x equals sine theta and y equals cosine theta. And notice, in this case, the parameter that I'm using is this parameter theta. So x is a function of theta, y is a function of theta as well. That's totally fine. It does not change anything. In the previous examples, we've used t. This time we're just using theta. But of course, we typically use theta to describe angles. And so this gives us some intuition about how we can think about these particular parametric equations. Now, I might want to graph this as well as figure out the direction in which my parametric equation is being graphed. So let's go ahead and set up a couple graphs here. Okay, so on the one hand, I'm going to, let's use, so on the one hand, I am going to graph my function. There we go. I'm going to graph my function x as a function of t, right? And that's just x equals sine theta. So sine theta starts at 0. And as we're only going, theta goes from 0 to pi. Let me change this t to a theta. As theta only goes from 0 to pi, I'm only getting this first half of the sine function, right? So I'm just getting that expression for my x coordinate. For my y coordinate, right, this is y as a function of theta. Since y is cosine, well, the cosine function starts up here, and as I go from 0 to pi, it's really going to come down here to a height of -1. Right, started up here at a height of +1, went down to a height of -1, and this was as theta hit pi. Okay, and now I could explicitly plug in some values, right? I know how to measure sine and cosine of a bunch of different, like pi over 2, pi over 3, pi over 6, etc. For the purposes of this example, I'm going to just eyeball this a little bit, and let's make some notes. So at time 0, right, so at time 0, I've got my x coordinate is equal to 0, and my y coordinate is equal to 1. So my x coordinate is equal to 0, my y coordinate is equal to 1. That means that at time 0, t equals 0, I'm floating up here. As I go forward in time, right, so the next moment in time I might want to look at is a point, let's say is this point right here, right, that point right there. My x value has increased a fair bit, and my y value has decreased just a tiny bit. So my x value is much larger than it used to be, while my y value has decreased slightly. If I go forward in time again, I could end up with, let's say, this point. Right here, my x value has continued to increase, but the increase has slowed down, while my y value has decreased a fair bit. So now maybe my point is right here. My x value has increased slightly, my y value has decreased a fair bit, but is still positive. And at this point, which happens to be pi over 2, we have sine of pi over 2 is 1, cosine of pi over 2 is 0. And so let's say that that is right at about this point here. And then we can do the same for the next few. Let me go ahead and graph those quickly. I'll plot 3 more points. So here, x value has decreased slightly, y value continues to decrease at a sharp amount, so we end up with something like this. X value has decreased, y value has decreased, right? And you sort of get a sense of what this is beginning to look like. And finally, the last point, I'll just use red, but I'll make it bigger. At pi, we have sine of pi is 0, cosine of pi is -1. and I am back here. So what has happened in this picture? Well, as I trace out from time equals 0 up to time equals pi, I'm getting a slightly lumpy, but imagine it much cleaner, semicircle, right? I'm going this way. I'm using these arrows to sort of indicate the direction of my parametrized curve, but this is actually going to be a semicircle starting at time equals 0, going to time equals pi, but it's tracing out the half of the circle that appears in the first and fourth quadrants. And that is awesome. That is so exciting. Very cool. Yes. Okay, so can we eliminate the parameter to find a Cartesian equation of the curve? Well, if I'm trying to find an example of the form y equals f of x, the answer is definitively no. I cannot do this, right? The reason here is because if I'm thinking of this as a function of x, my graph is failing to satisfy the vertical line test, right? Here's a vertical line, and it's hitting the graph of this parametric equation in 2 different points. So we cannot write this y as a function of x. But if I want to think of this x as a function of y, right? So if I want to think of my x value as being described from one of my, as a function of my y values, then yes, I think I absolutely can write this, x as a function of y. That would, the quote unquote vertical line test in that case would correspond to a line in a horizontal direction. And we see that all of these lines in the horizontal direction absolutely only hit this graph once. So in other words, this function, or this parametric equation, can be thought of as a function involving y, right? The variable y. Yes, awesome. So let's see how we can actually do this. So we want to play the same game that we did before. I'll bring my 2 expressions down. X equals sine of theta. Y equals cosine of theta. And now again, if my goal is to write x as a function of y, that means that I want to re-express this equation, turn it into a theta equals something, right? So turn that into a theta equals some expression involving y. And once I have that, I have theta equals some expression involving y. I can replace what's in here with my expression involving y, and then I'll get x equals sine of this thing involving y. We'll end up with some y's in there, and then we'll have our expression x, our expression x expressed as a function involving y's. So to do this, we have to recognize that as y, if y equals cosine of theta, then theta should be expressible as the inverse cosine or arc cosine of y. Check. And it's worth pointing out that our restricted domain here is absolutely necessary. So when we turn from y equals cosine of theta to theta equals inverse cosine of y, right? The cosine function is not normally invertible, but it is invertible on this restricted domain from 0 to pi. So this is a well-defined expression on the interval that we care about, and therefore we get, let me go ahead and sort of drag this way down. Since theta equals the inverse cosine of y, we get that x, when expressed as a function of y, is equal to sine of the inverse cosine of y. And if we want, we can try to simplify this just a little bit further. Okay, so to simplify this further, as a reminder, we've sort of talked through this a little bit in the past, but we need to do what we typically call a little bit of triangle magic, right? So as a little aside, I'll create a little box in which to draw the aside. Here's an aside. So if we wanted to draw a triangle, right? This is the same sort of picture we might have drawn back when we were doing trig substitution earlier in the semester. We can talk about an angle theta. My goodness, let's try that again. We can talk about an angle theta, right? And what we know is that y is equal to the cosine of theta, AKA I could label this side y and this side 1, so that the cosine of theta was equal to adjacent over hypotenuse, AKA y over 1, AKA y. So we have now that cosine of theta is equal to y, and we are interested in, oh, and therefore I should say theta is equal to the inverse cosine of y. And we are really interested in what is sine of the inverse cosine of y, AKA what is sine of theta equal to in terms of y? Well, sine of theta, as we know, is opposite over hypotenuse. And in our picture, our hypotenuse is 1. We just have to calculate this this opposite side. And the opposite side will be given by the Pythagorean theorem as y squared plus the opposite side squared equals 1 squared. And so that means that this opposite side must be, I'll draw it in a different color, must be equal to the square root of 1 minus y squared. Right, so sine of theta will ultimately equal the square root of 1 minus y squared divided by 1, aka just the square root of 1 minus y squared. So what is x of y? X of y is equal to the square root of 1 minus y squared. Cool. Okay, and that's going to do it for this video. Thanks for watching, and I'll see you all next time.